Okay, so welcome everyone to the second virtual International Solid Waste Student Design Competition presented by Solid Waste Association of North America. My name is Matea Vidovic-Klanac. I am member of SWANA Young Professional Steering Committee, and I will be your host for today's event. As we all know, the last couple of years were anything but conventional, but the students still rose to the challenge and have put together an incredible event for you today. We have students from 5 schools across the United States and Iran presenting today. The International Solid Waste Student Design Competition provides students with an opportunity to work on a real-life waste management challenge that our world is facing at this very moment. The competition strives to prepare students for similar issues they will potentially encounter after graduation, working as engineers or solid waste professionals. During the course of the competition, students have grown professionally as they strengthen skills in teamwork, problem solving, resource management, resourcefulness, and communication. But most importantly, each of them has begun their transition from students into the solid waste leaders of tomorrow. The students presenting today represent the next generation for SWANA and the waste industry as a whole. Young professionals are beginning to focus more and more on what is next, and are continuously bringing new, fresh ideas to the table. Young professionals are thinking big picture. They want to know what will happen with waste 100 years in the future, and more than anything, they want to be part of the initiative to make those changes. So what real-life waste management problem did the students tackle this year? This year, SWANA Young Peace wanted to address an issue that has been highlighted in recent solid waste industry news articles and is especially important to young professionals. The issue is whether the most important greenhouse emission source in the waste sector, landfill methane, is being estimated accurately using EPA's methods for calculating landfill gas emissions. An examination of EPA methods is needed since a proper accounting of landfill methane is critical for guiding our ongoing efforts in reducing emissions and maximizing the waste sector's achievements in addressing climate change. EPA's LandGem is well known, but uncertainties and potential biases in its estimates remain poorly understood, even after over 25 years of its use for reporting landfill gas emissions. The lack of understanding arises from limited ability to directly measure methane emissions. Until new methods such as remote sensing and drone monitoring are widely used, EPA is expected to continue to rely on landfill gas models to estimate methane emissions. To help students navigate the uncertainties, SWANA Young Peace provided project goals and recommended strategies for the teams to complete their work. The aim was to get students to develop an understanding of the issue that carried them beyond academic and theoretical considerations to reach solutions that accounted for real-world conditions and addressed the problem in a direct professional manner. Students were tasked to evaluate one or more EPA default methodologies for reporting landfill methane emissions and to estimate their potential bias. After completing their assessment of EPA methodologies, students were asked to propose alternative methods for calculating landfill methane generation and emissions that produce more accurate estimates for their study sites. This task was designed to spur students' creative as well as analytical thinking, as it asked them to attempt what the EPA has been unable to accomplish so far. So we are very excited about this year's event and look forward to the presentations by our student design teams. But before we get to the presentations, let me introduce our sponsor, our planning team, and our judges. So first, I would just like to thank our sponsor, the Hickman Endowment Fund, for the continuous support to the design competition throughout the years. So let's start with the introductions of the planning team. As previously mentioned, my name is Matea Vidovic-Klanac. I have been working as a solid waste engineer with SES engineers in Florida in our Boca Raton office for the last 4 years. Originally, I am from Croatia, where I graduated from the Faculty of Chemical Engineering and Technology and earned my master's degree in environmental engineering. I got an opportunity to come to the United States as a research assistant, where I joined Dr. Mirov's team at Florida Atlantic University and finished my second master's degree in civil engineering. I have been with SWANA Young Peace Steering Committee for about 4 years now and have been involved in leading and organizing the student design competition ever since. Next, we have Haley.
Hi, everyone. Good morning. I helped Matea put on this event as part of our SWANA steering committee. I have been in the solid waste industry for about 7 years, including an additional year actually in college. So much like a lot of you, I was involved in SWANA. I presented at a local SWANA conference. And then I graduated from Gonzaga, which I'm repping here today. And up in the Northwest, I graduated with a civil engineering degree and then went on to become an engineering consultant for the last 6 years. Now I work for Waste Management, one of the largest waste haulers in North America. So happy to kind of switch sides from consulting to the client side. I live here in Denver, Colorado, and I really enjoy being a part of SWANA to be a participant in things like this, where we're talking about industry challenges and connecting with one another across the country. So I encourage you all to stay involved in SWANA in whatever capacity that looks like for you. But we're happy to talk more about that at a later time. Feel free to reach out to me.
Thank you, Haley. Do we have Karam with us today? Okay, so Nate and Karam weren't able to join us today. So at this point, I would like the judges for this competition to introduce themselves. Who wants to go first? Hala?
Hi, my name is Hala Spear. I have a bachelor's in chemical engineering and master's and PhD in environmental engineering. I have over 25 years of experience in the consultancy world, and a couple of years ago started my own company, JHS Environmental Engineering. My focus has been solid waste and hazardous waste remediation work, just to simplify. Thank you. And I'm reviewing all these design projects. I have to say, everybody did an excellent job on preparing and researching this project. Alex, you want
me next? Okay. I'm Alex Stegey. I've been with the SCS engineers since 1990. I've been for the past 26 plus years, I've been specializing in landfill gas modeling for energy recovery purposes and utilization. I've developed models for the US EPA's landfill methane outreach program and their global methane initiative for their international outreach work, models for the countries of Colombia, Mexico, Ukraine, Central Eastern Europe, and Central America. I mostly work in the non-regulatory arena, so that I've been, SES has given me the freedom to do research on developing a landfill gas recovery model. So I also been the SWANA, head of the SWANA Generation and Modeling Committee from 2003 to 2015, and I was also the author of the SWEET model, the solid waste emissions estimation tool. And I do all the training at SCS engineers of model apprentices. So I am particularly enjoying this whole event. Thank you. David?
Thank you, Alex.
All right, good morning. My name's Dave Adams. I'm a senior vice president with Sanborn Head. I'm based in our Denver, Colorado office, like Haley. For the past 30 years or so, I've worked in medical waste, hazardous waste, and solid waste. I'm a waste guy. For the past 21 years, I've been with Sanborn Head, primarily working on air quality, permitting, modeling, landfill gas collection system design, and gas generation modeling. I'm a big advocate for SWANA. I've been involved with SWANA countless years. Back when I lived in Burlington, Vermont, I was on the board and eventually the president of the Northern New England chapter. For the 4 years or so that I've been in Denver, I've been involved in board activities right from the start, and I'm the current president of the Rocky Mountain chapter. And for YPs, young professionals, this is an exciting time at SWANA. These events, like the student design event, I was a mentor for the University of Colorado Boulder several years ago, and pretty impressed with the presentations and the reports that you folks have all done. So looking forward to today. Thank you.
Thank you, David. Please give a big thank you to all of these judges for dedicating a great deal of time helping with the solid waste student design competition. It could not have been done without them. So the presentations for today's event have been pre-recorded and will be played after introduction of each team. Then there will be a 10-minute questions and answer session where the judges and the audience can ask questions and students can respond. To ask questions, the audience can either raise their hand and we can unmute you, or you can put your questions into the chat box. We will try to get through as many questions as possible. The students have already been judged based on their design reports and posters. The posters can be viewed on the SWANA website at www.swana.org/SWDC. So the following teams will be presenting today in this order: Florida State University, Iranian University of Science and Technology, Clemson University, University of Texas of Arlington, and Jackson State University. So without further ado, let's get these presentations rolling. So first up, we have the Florida State University. So Florida team, if you can introduce yourself.
Hello, we're ACK consultants of Florida State University. I am Amy Sainsbury.
Hi, I'm Amanda Hare.
I am Kenneth Hills.
Montgomery.
Hi, I'm Cameron Dillon.
Okay, Estella, we are ready to play the presentations when you're ready.
Hi, my name is Amanda Hare. I'm a third-year environmental engineering major.
Hello, my name is Amy Sainsbury, and I'm also a third-year environmental engineering major.
Hi, my name is Cameron Dillon. I am a third-year civil engineering major.
Hello, my name is Kenneth Hills, and I'm also a third-year civil engineering major. And unfortunately, Colton Montgomery couldn't make it here to this presentation, but together we are ACK consultants, and we are here to present to you the evaluation of methane generation / emission models. Limitation of EPA's land gem model were evaluated using varying parameters for 4 landfills in different climates via other emission models. Methane gas is one of the most potent greenhouse gases and accounts for almost 1/5 of all the global emissions. Landfills are some of the most prominent producers of methane, so the inadequacies of land gem are an important issue that needs to be addressed immediately. Immense amounts of methane gas production could spell disaster for our climate, so improving the model for higher efficiency is paramount to achieving a cleaner and greener future for landfills. LandGEM is a generation-first model used to calculate the amount of methane that is created and secretly emitted from the landfill. The modeling of landfill generation is based on a small set of basic defaults known as K and L0 values. These values are far too broad to be used to accurately represent a wide range of climate conditions.
Oxidation is the consumption of methane by bacteria and other microorganisms who convert it into carbon. This aids in the reduction of methane emitted. For LandGEM, the default parameters for oxidation underestimate the amount of total oxidation that normally occurs as the gas travels through the covers. There are many different cover types, each of which have an expected oxidation value. The use of this small range of oxidation values given by LandGEM is detrimental to the overall methane emission estimation. The collection of landfill methane gas is a common way to reduce the environmental impact of landfill waste. The LandGEM maximum value for collected methane is 75% of the generated amount. However, landfills often collect more than 75%. This leads to a lack of incentive for landfills to collect as much as they are capable of.
LandGEM is the EPA's model for estimating the generation of landfill gases. The methane emission from landfills is calculated as a percentage of total landfill gas generated. However, many research advancements have been made since the creation of LandGEM. So this model is outdated and desperately needs to be revised. The methane generation rate, the K value, is determined by the moisture content, nutrients, and temperature of the waste mass. The higher all of these values are, the higher the generation rate will be. LandGEM's determination of the K values are solely based on the rainfall in the region, which is divided into two categories, above 25 inches per year and below 25 inches per year. These two categories are far too broad to be used to accurately identify the correct methane generation and emissions for the large range of landfills in the world. The potential methane generation capacity, LNOT, depends solely on the type and composition of the landfill. The higher the LNOT value, the more decomposable cellulose the landfill waste contains. This allows for more methane to be produced in the landfill. Due to LandGEM's excessive use of default values, the calculated landfill emissions are often not representative of the actual methane generated.
IPCC developed an alternative method that yields values that are based off the specific composition of landfill waste. These methods for creating different LNOT values takes into account more of the composition of waste and allows for the potential methane generation capacity to be based on the specific landfill. This is much better than LandGEM as it allows for the LNOT values to be more specified for each of the landfills based on the data found at the site and not just a range of default values. This is important as the LNOT value has a large impact on the generated value for emissions of methane from the landfill. This personalization of LNOT values allows for the landfill to have more accurate emissions, thus saving owners from costly fines and taxes on the emitted methane.
CalMem is an emission modeling program that uses field-validated data to produce more accurate oxidation and emissions for a specific landfill. This model uses the area and cover type of the landfill along with the location to get a more precise climate for each landfill. CalMem takes into account more of the parameters than any other model tested. This model is the only one tested that did not utilize a simple first-order equation to determine the methane generation and instead uses validated data to estimate a more accurate methane emission value. This model allows for more representative emission numbers, thus giving a heavy incentive for the owners to invest in better technology to collect and oxidize the methane generated in the landfill.
To begin with, we selected 4 landfills varying in climate which satisfied the following conditions: hot and wet, hot and dry, cold and wet, and cold and dry. The data for these landfills were then run through LandGEM using the default K and LNOT values. The next step was to run LNOT values from the IPCC model in LandGEM. Lastly, the area, cover type, coordinates, and total acreage were entered into CalMem to generate the model emissions. The emission predictions among the 3 models were then compared.
The methane emissions graph was generated from the LandGEM and CalMem models. LandGEM is a generation model, so the emissions were calculated via the equation generation minus the collected methane minus the oxidation to get the equivalent emissions for the year. CalMem is an emission model, so the values that are reported come directly from the program itself without any further calculations needed. This reduces the chance of accumulated error. However, LandGEM produced negative emission values, which implies flawed methodology.
The graph of the collection efficiency was compiled by placing the collected gas reported by the landfill over the gas that was modeled in each of the landfills. The collection efficiency are reported for Landgym, IPCC, site-specified K values, and efficiency reported in EPA's report. Each of values should range from 1 to 100% collection efficiency, but for the Tacoma City landfill, the gas collected was higher than the model. So the IPCC gas efficiency is over 100%. This just shows that the landfill created more methane than modeled by IPCC. The collection efficiency varied widely from 30% to almost 110%, but the values correlate well with the landfill reported values. But for almost all of the landfills, the reported collection efficiency was higher than the values that were calculated using collected over generated. For this reason, the collection efficiency was not able to be obtained for CalMin, as the values are only in emissions and the generation is required to obtain the collection efficiency.
Landgym has many pitfalls because the software was created to be non-site specific in its calculation of landfill gas generation. The modeling of methane in Landgym assumes that the landfill gas is composed of 50% methane, whereas it is possible that there could be more or less depending on the actual composition of the waste in the landfill. The lack of more specified K and L naught values also aids in this inaccuracy, as these are important in the calculation of total gas generated by a specific landfill.
IPCC aims to fix the issue of non-specific L naught values, as this model considers the specific composition of the landfill waste. This allows for the use of an L naught value that is more representative of the total waste profile, producing a more accurate generation value. While IPCC does address the issue of not factoring landfill composition into Landgym, it still uses the default K values, meaning the climate data continues to lack in this area.
CalMin aims to be the most accurate because it is not based on the generation of methane. It only focused on the emissions. While this model is the best of the tested methane, best of the tested models, it still has its own flaws, as the data is only based on area, not the depth of the waste. The CalMin uses data from the field to create accurate data for the landfill, but this is not specific enough for the data for the landfills, as the data for the landfills is generalized for the climate regions in which they are tested. Although the data is useful, the data set could be more robust, allowing for even more accurate data to be compiled.
The evaluation of Landgym shows that the model needs to be reworked to capture the varying conditions across many landfills. The limited number of default parameters used for Landgym leads to values that are not truly representative of the landfill gas production. The IPCC provides site-specific L naught values by factoring in the landfill composition. This improves the reliability of Landgym, as it is one of the important factors that methane generation is based off of. The CalMin model has an improved estimation of emissions, but it still has its flaws. Waste composition is not factored into the model, and as we know, this is an important factor in methane generation. The CalMin model also has a comprehensive oxidation modeling formula, unlike Landgym. All the models currently available are flawed in some way, as they need to be broad enough to apply to all landfills, but specific enough to accurately predict the methane emissions. Overall, methane generation and emission models are all inaccurate to some degree, and they will always have some degrees of error. Therefore, aspects from each model must be used to allow for an effective evaluation of methane gas emissions.
Thank you.
Thank you.
Thank you, Tim. So now we have open floor for any questions the judges or the audience can have.
Okay, well, I've been tasked to do the bulk of the questioning, but I'm sure David and Hala will chime in if they've got some additional questions. So for this presentation, I think you guys correctly understand that all models have flaws, and you certainly did a lot of work. I guess my first question has to do with your conclusion that the IPCC model there must be better than LandGem because it's a multi-phase model. It has 4 waste categories. So my question is, what happens if you don't have good representative waste composition data, which often is the case, and recognize that waste composition data are estimates based on sampling that aren't always representative. So I'm just letting you guys think about the possibility, a real life possibility, that your waste composition data are either not there or not representative of your site, and could actually potentially lead to error. So I guess this is just a question to comment on perhaps your ideas about the IPCC model versus LandGem.
So although IPCC model does factor in the different types of waste, if you don't have the obviously the specific type of waste or types of waste that are in your landfill, you will be better off going with LandGem due to the fact that you cannot get representative data. But if you have the actual data for your landfill with the compositions, then you are far better off going with the IPCC due to its factorization of the different types and decomposition rates of different types of waste.
Okay, thank you. I would point out, however, that we're the same way we're questioning the K and L0 values of LandGem, we need to question the same for IPCC. So it may be, even if you do have waste composition data, that those values in IPCC are maybe based on a relatively small sample of sites as well. And I think the IPCC was really set up for international application. And it was a big improvement during the period of the early 2000s when there was a big push for Kyoto Protocol projects to have a better model, and they were using LandGem and really creating problems. So, my second question really has to do more with your selection of CalMIM as your solution, and it does. The thing is that you kind of point out to an issue with CalMIM at the end of your presentation in your paper, which is it doesn't account for waste depth. And so it's kind of, let me explore that a little bit. Explain to me why that's a problem. Is it having to do with landfill gas generation? And if so, aren't we getting back to the issue of having to have a model to estimate how much methane is how much methane is being generated and produced and reaching the base of the cover soils? So how big of a problem is that issue? And could you maybe discuss what you think about that as far as limitations to CalMIM?
So I do believe that it is a huge issue because at different waste depths, you have different decomposition rates due to the exothermic reactions that may be happening in the waste. So therefore, CalMIM is not like the end all be all of the different types of models because it doesn't factor in the different depths at which decomposition rates change. So therefore, there has to be designed a better model to factor in all of those different decomposition rates.
Yeah, pretty much like what Colton was saying, we explored 3 models, and of those 3, kind of the pros and cons of each is what we were finding. And we didn't necessarily, of the 3 models, find one that was like set in stone, the one that we think is the best out there, because they each had things that were good and bad about them.
Okay. I don't know how much time we have left. Mateja, are we have more than we have?
We have
Finished
4
up.
more minutes.
How many?
4.
4 more minutes.
Yes.
Yeah, no, I would just comment on the CalMIM thing issue is really, I think the problem with CalMIM is it doesn't account for the methane flow to the cover soils. And that's something that you need a gas model to figure out, to predict. And so it's, that's kind of, you know, a pretty big glaring omission. The other problem with CalMIM was that you weren't able to test it with flow data because you could only test it with emissions data, and there is no emissions data. There's only emissions estimates. So the only data we have are the measured flow rates, in addition to the waste disposal estimates. So I'd go with another one unless David or Hala have something that they might be wanting to. I don't want to hog necessarily all the time.
One question I have is the data from the landfills. Were they closed landfills or active landfills?
Some of them were closed and others were open. For example, one of them we used in Phoenix, Arizona. That one was closed, whereas the ones we used in Florida were open. And so we had that variety.
Okay. I mean, it's typically hard to compare real data with what's estimated generated unless they're closed and you have a final cover and the age of it. Then you can really compare the data to the model prediction and see how it can be adjusted. Just as an FYI, operations really impact landfill gas collection efficiency. Although, for example, organic waste has a very high kinetic rate compared to other waste streams. Most of the time, by the time you cover it, most of the methane is gone by the time you cover it and you add the wells, the landfill gas wells. So just to point out that, but great job. I like the depth of it. David, any questions?
I don't think you have any further questions. No, thanks. Nice job.